This video will cover section 6.1, the first part of it, which is talking about slope fields. Previously, we were looking at differential equations and finding solutions to those by solving for y. And we called those separable differential equations because we could separate x and y and take the integral and then get an equation explicitly in terms of x. However, most differential equations you actually cannot do that with. So look at example 1 really quickly. dy dx equals x plus y. You can't separate x and y. You could subtract the x. The y. I just want to show you really quickly why that would work. So what I'm doing is I'm subtracting y over. So let's say that would be like negative y plus dy dx, and then that equals x. And if I try to move the dx over, I'd have to multiply the y by the dx. There's no way that I can actually separate the y and the x here. So this is a non-separable differential equation. So we can't get an equation for y. We can't actually solve for y here. But we still want to know something about what the curve might look like, or what's called the solution curve to y. Well, remember that if you have a differential equation, you have a derivative of y in some form. So what that means is the slope at any point on the graph is equal to dy dx. So what you can do is you can create this field of slopes, slope field, or sometimes it's called a direction field. And so you can, at each different point, you can kind of sketch out what the slope would be at that point, since you have a formula for the slope. And that's essentially what a slope field is. And then what you can do is you can find, now if I knew my particular solution, that is, if I know that my solution does have the point 0, 1 on it, for instance, then you can kind of sketch what the curve would look like, and you can make deductions from that curve. You can't get an exact equation or an exact graph, you can get kind of an estimation of what it would look like. So if I have dy dx equals x plus y, that means the slope at any point is going to be equal to the x coordinate plus the y coordinate. All right, so just really quickly, I'm going to go through and add up each x and y. So I'll do the first couple, explain those out, and then I'll pause it and do all of them at one time. So let's just choose the first point that I see. That's this point right here, which is negative 2, 2. And so if I were to add the x and the y, then I just get 0. So at that point, I'm just going to put a little line segment there of a slope of 0. So then you just do that for every point. Now, I want to make sure you understand here that this is a particular differential equation. So it's not like you always add x and y to the slope. It's just for this particular problem is x plus y. So let's just go across and do the next one. So that's negative 1, comma 2. So if I add those together, I get a slope of 1. So you just kind of have to estimate. What I typically do is I look at, if I were to connect a slope of 1, it'd be like connecting these two lines here. You don't want to do that, but I just wanted to show you that that slope on this graph would be like if we were to connect those two lines and kind of do an angle out that way. All right, then we come to 0, 2. So that would have a slope of 2. So again, it'd be like connecting these two lines. So you want that slope to have a steeper slope, but again, you don't want it to connect all the way down, just a little segment. And then finally, we would have the point 1, 2, which would be an even steeper slope of 3. So just as long as I see that that slope is getting steeper and steeper, that's fine. So go ahead, I'm going to pause the video. I want you to finish that slope field up for me. Okay, so this is what your final slope field should look roughly like. Again, it's just an estimation, so as long as your progression of slopes, you see that you're getting steeper and steeper as x increases. So now what you want to do with the slope field is you'll typically be asked to sketch the solution curve. Now, again, I want to make sure you understand the solution would be is if I were to able to find an equation for y, which is what we did in the last section where we solved a separable differential equation for y alone. Again, I can't do that here, so I can only sketch a curve, and they're going to give me a specific point through the point 0, 1. So we're going to go through the point 0, 1, and you're just going to follow the slope curve. So we know at 1 it has a slope of 1, and then as we continue on, it looks like we're going to start getting steeper. Now, you don't necessarily have to go through certain points. You just kind of follow along what the curve would look like. So then down here we're getting flatter, and then it becomes negative as well. Okay, so something like that. That's a pretty rough graph. I like to make it more smooth, so let's try that. Oh, sorry guys, hold on. Like that. Okay, so that would be a sketch of the solution curve for y for that differential equation. Okay, a little bit on notation. So it says in general, a differential equation is in this format. So dy dx equals capital F of x, y. So that function is just a function that involves both x and y. So that's just a notation that you need to be familiar with. A function in terms of both x and y. And it just goes on to tell you what a general definition of a slope field is. Okay, so now what we're going to do is we're going to match some slope fields. So given these two equations, we have a differential equation sine of x plus y, and then we have a differential equation sine of x minus y, and we have to match. Now, I apologize for kind of the roughness of this sketch. It's not very pretty. It was pulled off of a calculator, an old calculator, so it's not very, like I said, very pretty. But we can still tell a lot about these. So what you want to figure out in order to match these two equations is what I look for a lot of times is when the slope is 0. Okay, because you can kind of see these slopes of 0 here. So these little segments along here, you can see are 0, and there's some others in here involved. Okay, so you can kind of estimate where those slopes of 0 are occurring, because if I want to find a slope of 0, all I have to do is set my differential equation, my dy dx equal to 0, and see what that would be. So if I were looking at sine of x plus y, if I wanted that to be 0, if I want the slope to be 0, that is the slope, so I'm going to set that equal to 0. So then I think to myself, okay, when is sine equal to 0? Well, the easiest one to think is when the argument's equal to 0. So when x plus y equals 0. Now, obviously, there's a lot of points that make x plus y equals 0, but in general, if we solve for y here, you get y equals negative x. So when y equals negative x, you have a slope of 0. So if you look along the line y equals x, you can actually see that here. That looks like the line y equals negative x. So along those points, you have a slope of 0 when y is equivalent to negative x. So again, we can look at the same thing with the sine of x minus y. So same thing. If the sine of x minus y equals 0, that means x minus y equals 0. Solving for y, we get y equals x. So that means along the line y equals x, you can see in part B, you have slopes of 0 there. Okay, so that's something that when you're matching differential equations, that's something that I would recommend you look for is when you have a slope of 0. Okay. All right, and we've already answered B, which slope field goes with which differential equation. So we're good there. All right. So now the next question is, can you determine where pi and negative pi would be on the x-axis? So what that means is when x is pi, do we know where that occurs on the x-axis? So all you have to do is plug in pi in for your x. So we have the sine of pi plus y, and we're on the x-axis, so just kidding. If we're on the x-axis, we know that y is 0. So then the sine of pi would be at, hold on. So yes, if the sine of pi is equal to 0, then you know that pi is occurring where you have a slope of 0. So if you look back in, let's look at the x plus y one, you're looking at where you also have slopes of 0, and we kind of already were seeing we have this other line here. So when this kind of line of slopes of 0s crosses the x-axis, that would be right around in here. That's where pi would occur, because at pi you would have a slope of 0. And again, you could look on the other side and kind of see this line of slopes of 0 occurring here. So maybe around in here, you would have negative pi occurring. Okay? Okay, so looking at the next graphs that match, or that we're trying to match, we have the sine of x cubed and the sine of y cubed. Now, instead of having x plus y and x minus y here, notice that for one, it's only in terms of x, and the other is only in terms of y. So if the slope is dependent on something that's only in terms of x, that means that as y changes, there's no change made to the slope because there's no dependency on y. So let me write that down. So the first one, x cubed. There's no y involved. So as y changes, and x stays the same. I should probably say that. And x stays the same. Slope does not change. Okay, and same for the y. As x changes, but not the y. Just ditto there. Okay, so what you're looking for is what I tend to do. So if I'm looking at the x, so it rephrases it down here in part A. We're looking for a graph that depends on x and not y. So as y changes, we're looking for a slope staying the same. So y changes vertically. So if I look up and down and the slope stayed the same, then you know that it's dependent only on x. So looking at A, if I look up and down, those slopes are changing all over the place. So that is definitely not dependent on just x. But if I look at part B and I look up and down, as y changes and x stays the same, my slope is staying the same. So B is depending on x, but not on y. And then if you look at A, if you look at as x changes, but y does not change, my slopes are staying the same. So that's dependent on y, not on x. Okay. So that's another way to look for it. So those are the two from example 2 and example 3. Those are the two things that I would look for when you're trying to match graphs with their differential equations. So look for when the slopes are 0, and also if it's only dependent on x or only dependent on y. Okay? All right. So looking at the final example, this is where we have the full matching thing. And you can see that our differential equations are very similar. We're all dividing x by y, but we have y divided by x or x divided by y, and then we also have the positives and the negatives. So what I would look for here is looking at slopes of 0 and undefined slopes. So for instance, if you have y over x, then you would have a slope of 0 when y equals 0, and you'd have a slope of undefined when x equals 0. Okay? So in other words, y is 0 on the x-axis, and x is 0 on the y-axis. So for y divided by x, along the x-axis you have slopes of 0, and along the y-axis you should have slopes of undefined. So the first graph here, we have along the y-axis our slopes of 0, so that's not going to be it. And also the last graph is not going to be it. So we're looking between these two graphs here, because if you look along the y-axis, you really don't see any graphs. So that shows that you have an undefined slope. And if you kind of follow the sketch of these curves, it looks like it's going to be fine. And then along the x-axis, you can see again that these slopes are coming towards 0. So these two graphs would be the candidates for A. Okay. And so the other candidate would be for C. So these two graphs that I'm looking at right now would be between A and C. So now we need to figure out okay, which one's negative and which one's positive. Well, if y and x are the same value, so that means along the line y equals x, we would have a slope of positive 1 for part A and negative 1 for part C. So if I look along the line y equals x, you see those are slopes, those are positive slopes. And if I look here along the line y equals x, then those are negative slopes. So this bottom one would go with the negative y over x, and the top one would go with the positive y over x. Okay. So then if you look at B and D, that's just going to be the opposite. So for B and D, when x is 0, that's along the y-axis, then you're going to have slopes of 0, which you see that here and here. Okay? And then the same thing with the negatives. Along the line y equals x, if you look there, when x and y are the same, you have slopes of 1 or negative 1. So in D, those are negative, and for B, those would be positive. Okay? So that is slope fields. So the main thing that you'll see with slope fields on a test is, can you draw a slope field and sketch a solution curve like this? So that's something that you'll see And then also, you would have to match a graph with the differential equation.